So this is lecture number 11 of this heat treatment class, and we'll discuss the same thing, that is precipitation strengthening. So we'll stick to that topic, and already you have started talking about these things. Isomorphous system and two-phase alloy system, right? Now, also we have talked about this, how precipitation strengthening will be there, and what are the different precipitates we can have. And today we'll see again this is a very interesting figure. Just look at this figure. This is again, you can see we have an you can say this is an which kind of system we have? Eutectic system. Very good again. So you can see this is again, you can see this is the terminal solid solution alpha, and this is the terminal solid solution beta here. And this is liquid, and this is two-phase region. This is two-phase region, but this is completely two-phase solid region, alpha plus beta. Look at these points. This point, I'm talking about this point. Suppose this is the room temperature. This is the room temperature. You understand, this is the temperature axis, this is the composition axis. And this is the room temperature, for example. So at the room temperature, this is the maximum solubility in alpha phase. Right? Solubility limit at room temperature is written over here. And suppose I am taking an alloy of this composition. Listen it carefully. I am taking an alloy of this much of composition. I'm drawing a projection here. At room temperature, listen it carefully. At room temperature, the alloy will be having an equilibrium microstructure. This is the equilibrium microstructure of the alloy of, suppose, at this composition. So what can you people tell me, what you can able to see here? Just tell me quickly what you can able to see here.
Green color are precipitates along the grain boundary.
Yes, very good. We can able to see grain, and this green color are the precipitates along the grain boundaries. Very good. So since this is a two-phase alloy, so one phase is, suppose this grain is alpha, and this green color precipitate is beta. Fine. So now what you do? You are doing solutionizing. Solutionizing, you remember, you are taking the alloy to a high temperature where we will have a single phase region. Suppose I am taking the alloy to this point. So this is a single phase region alpha. So do you anybody remember what is solutionizing physically means?
Complete solubility.
Yes, complete solubility of what?
Precipitates.
Precipitates, yes, everything. If anything
Everything.
will be there, any second phase will be there, basically you can call any second phase will be there. Any carbides, nitrides, carbonitrides, or any second phase, they will become soluble. So finally, when they become soluble, it is kind of a solid solution. So this is forming, you can see. So this is again having only single phase, only grain and grain boundaries. This precipitate has been dissolved in this region, alpha phase region, right? So now you are doing quenching of it. So what is the result microstructure? This is the again same result microstructure. Again, it is a solid solution. There is no second phase after doing quenching. That means I will quench from this temperature to again room temperature, for example. Here, first I take the sample to this region, and I have to hold it. That is called solutionizing heat treatment. That means all the second phase particle will become soluble. That means if there is any precipitate, they will become completely soluble. A single phase will form. From here, again, I will quench it. I am doing rapid cooling to room temperature. The microstructure is this one and this one. So finally, I am getting what? Super saturated solid solution. Fine. So I think you people have understood up to this. That means what? That means it is written over here. Just look at this figure. From this part to this part, you understand at room temperature, the solubility limit is this much only. But I have taken an alloy of this much composition and I'm heating it to this temperature, then I am quenching it again or rapidly cooling it to the room temperature. So that means I am keeping a lot of solute atom in my matrix now. A lot of solute atoms will be there in dissolved form. So that is why it is supersaturated solid solution. It is a solid solution but supersaturated one. So I have written from this end to this end, it is excess amount of solute atoms in solid solution. You understood? Everybody have understood now? This is the excess amount of solute which is present over here, because this is the solubility limit. But now you are putting lot of solute atom into this matrix phase. So this part is clear, you understand, right? Okay, suppose I will take this material, then I will have which kind of strengthening? If I have this is the final product, for example. So I will have which kind of strengthening?
Transformation strengthening.
Transformation strengthening, how you can say transformation strengthening?
Solid solution strengthening.
Solid solution strengthening, very good. Everything is in the solid solution. Transformation, we should not be confused. Transformation strengthening basically means austenite phase will be becoming some other phase which gives strengthening, like benite or martensite. Right, those are basically called transformation strengthening. But here you can see only solid solution now. Now you people understand? You got the point that this is a solid solution. So you'll have a solid solution strengthening. Suppose I will take this material and I will allow the material to stay for suppose 5 days at a relatively low temperature, suppose 300 degrees centigrade, or suppose it is a steel, suppose I am putting it for a 500 degrees centigrade or 450 degrees centigrade. What will happen? Can anybody remember? If I will allow the steel to remain for 5 days, 6 days at suppose or for 2 days at 500 degrees centigrade. If this is steel and if this is an aluminium, suppose I am putting it for like at 250 degrees centigrade or 350 around. What will happen?
Sir, high strength.
Why high strength?
Sir, age hardening.
Age hardening will take place. So what will happen again?
Formation of precipitates.
Formation of precipitates will again
Yes, sir.
take place.
Yes,
Very
sir.
good. Initially, if this is supersaturated solid solution, we are having a solid solution strengthening only, because everything is in the solid solution form. There is no second phase particles. But if you allow the material to be there at a relatively low temperature for many hours, for many days, precipitate will start forming in the materials. Second phase particles will come out from the matrix. It may form inside the grain, or it may form along the grain boundaries, or it may be uniformly distributed throughout the material. So that material, that name is called what? That means after doing solutionizing treatment and quenching, I am getting supersaturated solid solution. So next stage will be what for precipitation? What is the name, technical name of that? What is the technical name of that? Can you figure it out here?
Yes, sir. Aging.
Aging. So you understand what is aging means now. Aging means you are allowing the material to be there at a relatively low temperature without disturbing it. Right? So precipitate will start forming during aging process. Right?
Sir, what is the benefits here?
What is benefit
Because,
means?
we have our precipitate in our first stage. Later on,
Okay.
we are getting the same precipitates. So what is
Okay,
the benefit?
fine. The benefit is that these precipitates may not be uniformly distributed when you are doing melting and casting. You are making an alloy means at the end you are doing melting and casting, right? You'll get a cast product, for example. In that cast product, it doesn't mean that all the precipitate are of uniform size, all the precipitate are of smaller size, which you want, desirable size, or the distribution of precipitate may not be same everywhere. You understand now?
Yes, sir.
You might end up with bigger precipitates, non-uniform distribution of precipitates, and precipitate of poor properties you might have after casting. So you need to do what? You need to again heat at this temperature, again quench it, Then you do edging after that. What will happen? Uniformly precipitate will form everywhere, maybe, right? And that may be of required size which you want. If edging time will be more, precipitate size will be also more. You have to remember that. You understand? If you give a less edging time, precipitate will be very small. If you allow for an intermediate time, precipitate will be becoming bigger. But if you allow more enough time for the edging, then you can get a more bigger size precipitate, which are not actually required, which are detrimental basically. Very big size precipitate are not good. So you understand how to get precipitation in an alloy. So you people can write in an examination how to get an precipitation in an alloy by drawing this kind of diagram. You'll get a question definitely from this part. So already I have written over here. Supersaturated solid solution by taking the sample to a single phase region, then rapid cooling it to two-phase region, because you understand this is the two-phase region, alpha plus beta, and this is a single phase region. Solutionizing is done at a single phase region, but quenching will be done to the two-phase region. Fine. Then you have to wait for the precipitation to occur. Wait means you have to wait means what you are doing. You are doing edging, right? And you have to remember there are two types of edging. One is natural edging, one is artificial edging. Natural edging means if you allow the material to be there in the room temperature for a long interval of time, automatically precipitate will come out. Artificial edging means intentionally you are taking the alloy to a relatively low temperature. As I told, in case of steels, you can take it to 450 to 500 degrees centigrade. For aluminum, you can take it to 250 to 350 degrees centigrade. You understand now? Okay, next, just this is an aluminum copper phase diagram, binary phase diagram, aluminum copper, but this is not a complete phase diagram, right? I'm not showing the this side end, complete this side end, right? So you understand this is a single phase region, and you are quenching the aluminum copper alloy to this two phase region, alpha plus beta. That is solutionizing. Then you allow the aluminum copper alloy to be in the edging temperature, for example, 250 to 300 degrees centigrade, precipitate will start forming. Similarly, here copper zinc system, you can see this is a single phase region. You are taking your alloy to this region first, then you are then quenching it or rapidly cooling it to this two phase region, right? Now this is a free energy versus R, radius of the precipitate. How many of you have remember? Let me see. This is completely related to your nucleation and growth part. While I was talking about those phase transformation, solid liquid to solid phase transformation, but here it is actually a solid to solid phase transformation. A nuclei will form from a matrix. Can anybody remember what is this showing? Just look at this image and tell me. This free energy axis, and this is the radius of the precipitate which is forming. Suppose this is the radius of the precipitate which is forming, and this is the matrix phase. Just try to figure it out. How many of you have remembered this equation? But some additional things are here actually. How many of you have remember what is the free energy change on transformation from liquid to solid?
Yes, sir.
When liquid will transform into a solid, it will go through nucleation and growth stage. Everybody have remember, right? So when a solid nuclei will form from a liquid, what is the change in free energy? Delta G. What are the two different terms we have in that? It is over here. Just look at this one at least.
Sir, volume free energy change and the surface
Very
energy.
good. Volume free energy change and surface free energy change. From volume free energy change and surface free energy change, which one is positive, which one is negative? Let me see how many of you have remember.
Surface is
volume free energy
positive and
change
volume is
or
negative.
surface free energy?
Yes, very good. Surface free energy change is always positive because you are creating a new surface, right? You are creating a new interface between your matrix and precipitate here, right? So here it is positive. And this gamma is nothing but your interfacial energy, if you remember. And this is the formula of your surface area. because we are creating a new surface, and that is spherical new surface. So 4 pi r square. And this is the volume of the spherical particle or precipitate, 4 by 3 pi r cube. And this is the volume free energy change per unit volume, delta GB. And there is an additional term. This term, do you think this, do you remember this term was there or this term was missing in that condition? When a solid nuclei is forming from a liquid, this term was there or it is missing in that condition? This was missing, yes, this was missing, only this term was there. This term is there because of strain energy. You have to remember, strain around the particle. Here a precipitate is a solid particle and this forming on a matrix. So it is creating a strain field around the matrix, lattice of the matrix. So that's why additional term has to be deducted from this part. But when we are discussing about solid to liquid to solid transformation, we are not having this kind of strain energy, because we are considering density of the solid and liquid is same. Volume change is same. Volume are same, you can understand. Okay, anyways, here already I have written del GB minus psi means we are removing some volume free energy change because of strain generated due to formation of a particle. Okay, fine. So now, how many of you remember this plot? Here it is r cube and this is r square. Now you are getting something? R square and r cube. Yes. This is the hint. R square, r cube. Okay. How many of you can say when a precipitate will form from a matrix, what should be the condition? If this is the overall free energy change during this transformation, this term should be negative or positive?
Negative.
Negative. Very good. This term should be negative. Delta G should be negative if a transformation will be possible. But now this is r cube and this is r square. Now, do you remember this one? R is the radius of the particle. Now you are getting, and this is a free energy. When r is small, what will happen?
So when r is small, the positive term is dominant.
Very good. That means surface area term will be what?
That is the dominating term.
Dominant or bigger term, right?
Yes, sir.
So this delta G will be what? Positive? Yes or no?
Sir.
Yes, sir.
But when after sometimes when the particle size will be more bigger and more bigger, it will reach a particular r value, that is r star. Now you remember critical size of nucleus, right? And the corresponding free energy G star. So after this size, if the size will become more bigger, then which term will be dominating?
R cube is dominating.
R cube term will be dominating. Very good, because this is cube, this is square, right? So volume term will be dominating, and volume term will be a negative term. Now del G will be what? Positive or negative?
Negative.
Negative. So that's why what is happening, you can see the graph is going downward towards which? This is the negative part. This is the positive part, right? So initially when the R is smaller, so if the R will be, suppose R size will be this much, what will happen to the precipitate? Can anyone tell me? If a precipitate will form of this size, what will happen to the precipitate?
Sir, it is not stable. So it will.
No, it is not stable. What will happen? It will again dissolve into the matrix. Very good. If the size of the precipitate will be this much, then what will happen?
Growth will take place.
Very good. It will start growing. Very good. You have remembered that, right? So R star is the critical size of the embryo or nuclei which is formed, right, in the matrix here. So now this is an important term. You have to remember from this part, I am getting a conclusion. This one actually, this is our final conclusion. So G star is proportional to gamma to the power q, interfacial energy. You can term this is an interfacial energy term, and square term is this one, chemical free energy or volume free energy, you can say. So that means which one is more dominating then? That means G star will be mainly depend upon this term, this R cube term, yes or no? Interfacial energy term is more important now. or interfacial area. More is the interfacial area, more is the interfacial energy, right? So here it is written, G star is very sensitive to the interfacial energy because this is R gamma to the power cube. Gamma here means your interfacial energy here. Now coherent and incoherent precipitate. Achha, how many of you have heard this term earlier? Have you ever heard this term, coherent precipitate and incoherent, or coherent interface and incoherent interface? Have you ever heard about this term? Yes, Soumya?
Yes, sir.
Which subject you have heard that?
Phase transformation.
Okay, phase transformation. So you are already done with this topic, phase transformation. Already you have covered this topic, I mean subject.
Yes, sir,
Yes.
but not complete.
Okay, that means in this semester you are having that subject. This subject is going on right now, or it is already over?
No, in the previous.
Oh, in the previous semester you are having that subject. Okay, very good. Anyways, so we may have a coherent precipitate and we can have a incoherent precipitate, and there is another in between precipitate that is called semi-coherent, but we will not discuss that. So precipitate, which is a particle which is formed on the matrix, it may be inside the grain or it may be on the grain boundaries. That precipitate may be a coherent or it may be a incoherent, or in between them, that is called semi-coherent precipitate. The interface is called coherent interface, and interface may be incoherent, right? So what is exactly that? I will discuss that here. Just look at this image and look at this image. What difference? Let me see what difference you are getting. Just tell me quickly, huh? And it is written over here. Dark lines are the lattice planes or the atomic planes. These dark lines. Huh? Yellow is a precipitate. This is a precipitate and this is a precipitate, yellow part. And light pink. Sorry, this is not actually light pink. Which color it is visible to you? This one? This color?
Brown.
Brown. Actually, if you change your position, the color is changing, right? If I will stand right now and I look at this one, it is looking at light pink. But if I will sit and I look, this is looking like something light ash color, I think.
Gray,
brown,
sir.
Gray color, yes. Otherwise, I'm writing gray. Light gray. Light. So this is your matrix. This is your matrix, gray color. And this yellow part is a precipitate. And these lines are atomic line or lattice planes. Now, can you figure it out? What is the difference between here and here? Tell me quickly. But looking at the figure, you can tell me. First, tell me about the precipitate. Tell me about the precipitate. What is the difference you can able to see? It is a small, right? Yes or no? The precipitate is smaller in size. And here it is bigger, right? Bigger size precipitate. Is it okay now? Any other difference? Okay, this is one difference about precipitate. What about the lines? Can you tell me? Atomic line or atomic planes?
Sir, in coherent they are nearly matching, but in incoherent some lines are not matching.
Matching. Okay, this term is matching, but for a just what is the difference you are getting? Just tell me. Matching means what you are saying exactly. Anybody want to speak anything? What is the difference between these lines and here in these lines? Carefully look at the lines.
Sir, in the coherent, there are all complete lines, but in incoherent, there are some line breaks.
Yes, yes, very good, very good. So continuity. Continuity in the lattice plane. Right? Now you people understand? there is a continuity in the lattice plane across what? I should write across what I should write?
Precipitate.
Precipitate, only precipitate, or across precipitate matrix interface? It is okay now? So you can see the lines are continuous. This line means this is a atomic plane is continuous. Atomic plane starting from the matrix to the precipitate, then to the matrix is continuous, right? There is a continuity is there. But here it is, what I should write? Not continuous lattice planes or atomic planes. Across the interface. So what is present? Dislocation. Can you able to see a dislocation there? How many of you can see dislocation? Can you able to see dislocation here in this image? It is clearly visible.
Yes, sir.
Where
The
there is
red box.
discontinuity, where there is discontinuity, there is an extra half plane of atom here, and this is an extra half plane of atom here. There is a discontinuity, right? There is no continuous plane here. Here also there is no continuous plane. Here there is no continuous plane. Some planes are there, but we are having dislocations across the interface. So this is the difference between coherent interface and incoherent interface, or coherent precipitate and incoherent precipitate. The first one is size difference. Basically, bigger size precipitate are incoherent. Smaller size precipitate are coherent. Like GP zones. GP zones in aluminum copper system. Those are coherent precipitate. But the last precipitate which forms basically is incoherent. That is basically aluminum copper. L2Cu or AlCO2. What is that? And this lattice plane are continuous and these are discontinuous lattice. We are having dislocations here, right? So basically there is an interesting fact you can remember. Coherent precipitates have low interfacial energy, right? Low activation free energy, so easy to nucleate. So coherent precipitates are always easy to nucleate. So that is why in aluminum copper system, GP zones first form, because they have a low interfacial energy. So you understand, if something have a low interfacial energy, so low activation free energy is there. Already I have explained this one. Now you people understood? If this will be small, what happened to this one? What happened to this one if this will be smaller?
This
will be small.
will be small.
If this will be small, what will happen? You can see. So that is why. Yes. That is why coherent precipitate forms easily or easy to nucleate. But in case of incoherent precipitate, high interfacial energy is there. So high value of activation free energy, and finally very difficult to nucleate. So coherent precipitates are always easy to nucleate. So next is, you can see same figure I have drawn here. I have also written same thing. Low value of gamma, low activation free energy, easy to nucleate. Everything I have written over here. Here it is interesting fact. If precipitate is coherent with the matrix, it means interfacial energy is small, then it is easy to nucleate. If the precipitate have a lot of structures in it, lot of structure means dislocation structure at the interface, that is incoherent, and the interfacial energy will be more, then precipitate will be difficult to nucleate. So difference between the interfacial energy is also there. Here interfacial energy is less, here interfacial energy is more, right? Now, how there are other interesting facts are here. Basically, in complete coherent precipitate, the crystal structure and the lattice parameter of the precipitate are same as the matrix, and difference is in the chemical composition. So that means if your precipitate which is forming on the matrix have same crystal structure as the matrix and same lattice parameter, they basically form a coherent precipitate, right? You have to remember that. Someone is saying 1-to-1 bonding. 1-to-1 bonding. Bonding between the atom is 1-to-1. Here to here. But can anybody figure it out? What is happening to this one? This line should be straight one, but this line is not straight. Why?
So lattice parameter is not same.
Yes, very good. Lattice parameter is different in the precipitate. That means lattice parameter of the matrix and the precipitate should be nearly same. But sometimes what happens, the crystal structure may be same, but lattice parameter is slightly different. So that's why there is a bending, right? There is a bending of the lattice plane inside the precipitate is happening. But this bending and this bending, what is the difference? Here the bending will be more and more with bigger size precipitate. If the size of the precipitate will grow more big and more bigger, so what will happen? There will be a lot of strain will be there, right? Because lattice parameter of this one and this one is not matching, so there will be more bending. If there will be more bending, more strain will be there. So at the end, what will happen? Dislocations will generate in this material. Like here, this is dislocation, this is dislocation, right? Okay, anyway, so what I am discussing is strain but coherent precipitate. So this is an example of what? Completely coherent precipitate or strain but coherent? This is an example of coherent, completely coherent precipitate or strain but coherent precipitate.
So strain but coherent.
Yes, obviously. Why strain? You understand. Lattice parameter is different, right? So there is a bending of the lattice plane is inside the precipitate. That is the reason. Okay, anyways, very good. So here basically lattice parameter is different, but crystal structure are both are same, due to which lot of strain across the interface will be there. Lattice plane looks like bending inside the precipitate, which I have written over here. Then incoherent precipitate. Incoherent precipitate generally assumes spherical shape to minimize the interface. So since they have high interfacial energy, so they try to take a always spherical shape. And basically the crystal structure and lattice parameter are different, you can say. Now this is the interesting one, dislocation, precipitation, interaction. This is our main topic because this interaction will lead to strengthening. So two ways are there by which dislocation will interact with the precipitates. So dislocation is moving, and how it is interacting with the precipitate, that is two ways are there. So one way is what? Shearing will be there or bowing of the dislocation will be there. Either shearing will happen or bowing of the dislocation will be happen around the precipitates. Here shearing also means cutting. Either dislocation will cut the precipitate or dislocation will get bow around the dislocation, around the precipitate, right? I'll show you the image. I have that. Let me show you this one. So suppose this is a matrix, for example. This is a matrix. And what is this? This is a precipitate. And this is a slip plane, for example. Can anybody tell me what is this part?
An edge dislocation.
Edge dislocation. So edge dislocation is gliding in this direction and it is meeting a precipitate. So what is happening? You can see. But this next stage is saying what? Can anybody tell me?
So cutting.
Cutting, very good. So dislocation will cut the precipitate into two halves. So this is one half and this is another half. Now carefully look at this image and tell me what is happening to the surface area and surface energy after cutting and before cutting. This is the image of before cutting. Dislocation is present over here. Dislocation is gliding and cutting the precipitate into two halves, right? So which is the image of this one? Dislocation is getting cut by the, precipitate is getting cut by the dislocation, and dislocation is now free to move. It is gliding again in this, and it is here. So what happened to interfacial energy and interfacial area before this and
increase?
Increase. How you can say increase?
So data surface generator.
Very good, very good. You can see this is the new surface area, this part from here to here, right? And from here to here also a new surface is created. Yes or no? This is the new surface area and this is the new surface area. So surface area will be increasing and interfacial energy will increase, obviously. So this is the real image. You can see a dislocation is moving and cutting the precipitate into two halves. This is one half and this is the bottom half. Top half, bottom half. You can see. Earlier precipitate are like this. The same precipitate is also here and it is getting cut by the dislocation. So this is one kind of interaction of dislocation with precipitate. I'll tell you what is the condition of this. I'll discuss the slides. You can see another kind of interaction. This is also very good interaction. This is a dislocation you can see. And this is one precipitate. This is another precipitate particle. There is a distance between them is L from center of this one to center of this one. And this distance is L minus 2R, obviously. So dislocation is moving. But dislocation is moving, but dislocation, how dislocation is interacting? Dislocation is getting bowing. You can see bow around the precipitate. This is getting bow around the precipitate. Finally, what will happen? This will become a loop because this end and this end are having different sign, and this end and this end will be having different sign. So they will annihilate each other, and finally they will form a loop around the precipitate, and dislocation is free now. Then it will again glide. So can you people figure it out? Suppose this is the first dislocation is moving like this and forming a loop around the precipitate, and it is going out. This is called Boeing mechanism. Suppose a new dislocation will come. For a new dislocation, distance between the precipitate will be less or more, or it is unchanged.
Less.
Yes, less. How less?
Sir, loop create ହେଇଗଲା ମାନେ
Very good. A loop has been already created, so distance between them will be decreasing. So you have to remember, if distance will be decreasing, bowing will be difficult. The dislocation will, you have to apply more shear stress to bow the dislocation. So obviously strength will increase, right? Same things I have explained
Hello,
over
sir.
here. Yes.
that the previous slide.
This one or this one?
Next one.
This one.
सर एमती गोटे डिस्लोकेशन कला बोइंग कला एमती जदि जाय कि बार बार मेंचे गोटा लूप क्रिएट हे गला दुईटा को लागी गला एकाथरे ताहले कोन हबो नेक्स्ट डिस्लोकेशन आसिले से आ जाय परिबनी
Listen to the question carefully. Listen to the question. I have asked if what happened to the next dislocation. Suppose next dislocation is coming, but next dislocation cannot go easily. It cannot bow like this. It will be very difficult to bow. You have to apply a lot of stress to bow it down again. Suppose you just assume that second dislocation also have passed away. So another loop will form. Distance between the two precipitate will be more decreasing, right? So third dislocation cannot move. So finally fracture will happen. What will happen? If stress will be very high and dislocation cannot move, finally what will happen? The result will be fracture of the material. You understand now?
Yes, sir.
But I cannot say that how many dislocation can cross. I don't have much idea that 3 dislocation will cross or 4 dislocation will cross or 10 number of dislocation can cross. I have no much idea about that exactly. But you should understand the concept. The concept is if one dislocation will pass away, it form a loop and distance between them will be decreasing. So next dislocation cannot easily pass through this by bowing, right? Since the distance is decreasing, you have to apply more stress. Suppose second dislocation has crossed away, again distance will be decreasing. Okay, anyways, so finally, yes. So what is the condition now? Condition when the dislocation will bow and dislocation will cut. What should be the condition? So condition are written over here. If precipitate is coherent, shearing or cutting will take place. But if the precipitate is incoherent, bowing will take place. So can you people tell me, if precipitate will be bigger and smaller, what will happen? If the precipitate size will be small, what will happen? If the precipitate size will be big, what will happen?
So bigger hele Boeing haba.
Yes, very good, because it will be incoherent kind of thing.
Cutting.
If the small will be there, it will be cut or sheared. And if the particle are weak, then it will get cut. If the particle are strong, Boeing will occur. This is another condition. Coherent small precipitate dislocation interaction. If the precipitate is small and coherent, how it will interact with the dislocation. Here, when the precipitate are small and coherent, spacing between the particles is small, due to which Boeing will not take place. It's required more energy. So dislocation will shear the particle. Second one is consequence of shearing, cutting of particle. New interface is created between the particles and matrix due to the due to this interfacial area increases, lead to increasing in the interfacial energy, which gives rise to strengthening. So if a new dislocation moving on the same slip plane, find it difficult to cut it. Fine. Same thing. Now, large and incoherent precipitate dislocation interaction. Same thing I have written over here. 4 stages. Stage 1 is dislocation is close to the particle. Dislocation Boeing between the precipitate. Then with more shear stress leads to more Boeing of the dislocation around the particle. Finally, due to opposite Berger vector, sign of the dislocation two will annihilate each other and result in leaving a loop around the precipitate, and dislocation will cross away. So this is called R1 mechanism. So R1 mechanism is similar to which mechanism already we have studied in strain hardening part. Can anybody figure it out? This mechanism is resembles to which kind of mechanism?
Dislocation multiplication.
Very good. Dislocation multiplication, like a Frank Reed source. Very good. So this is dislocation cutting the particle. Creating new surface. So that leads to more interfacial energy. Now, can anybody conclude this topic? How strengthening is happening if a small precipitate will be there, and how strengthening will happen if a big precipitate will be there, or how strengthening will be there if a small precipitate with coherent precipitate will be there and big precipitate with incoherent precipitate will be there. How strengthening is happening? Tell me. Anybody want to speak? Can speak.